All right, let's jump right in. When you think about the building blocks of life, you probably picture something that's like everywhere, right? Super common. But what if I told you the architect of, well, everything, the element behind every single living thing, is actually a total cosmic underdog? Yep, today we're talking about carbon, the unsung hero of, well, existence itself. And this is the central mystery we're going to try and unravel today. All life, from the tiniest microbe to the biggest whale, it's all carbon-based. And yet when you actually look at what our planet is made of, carbon is shockingly scarce. It's this wild paradox that sits right at the heart of biology and chemistry. Get a load of this number: 0.02%. That's it. That's the tiny, tiny slice of the Earth's crust that's made of carbon. It's practically a rounding error. And yet, from that ridiculously small amount, the entire symphony of life has been composed. So, how in the world does it pull that off? Well, to understand that, we gotta meet our hero properly. Carbon is a nonmetal, and its whole identity, its whole story, really boils down to one single number. And that number is 6. Its atomic number is 6. That means it's got 6 protons and 6 electrons. Now, 2 of those electrons are tucked away in its inner shell. But, and this is the important part, 4 of them are in its outer shell. In the world of atoms, stability is the name of the game, and you get that by having a full outer shell, which usually means 8 electrons. So for carbon, with its 4 outer electrons, this is a massive problem. And this one simple fact leads us to the core conflict in our hero's story. See, to get stable, an atom usually wants to do one of 2 things: either give away its outer electrons or snatch some from another atom. But for carbon, neither of those options really works. So here's the deal. Carbon is basically stuck between a rock and a hard place. Look at its 2 options, right? Option 1, it could try to lose all 4 of its outer electrons, but that would take a massive amount of energy, way more than it has. Okay, so scratch that. Option 2, it could try to gain 4 electrons from another atom. The problem there? Carbon's tiny little nucleus with just 6 protons just isn't strong enough to hold on to 10 whole electrons. The atom would be completely unstable, so it can't give and it can't take. It looks like a chemical dead end. Or is it? This is the moment our unlikely hero discovers its first superpower. When giving and taking are completely off the table, carbon finds a third, much more elegant solution. It decides to share. And we call this covalent bonding. Instead of this hostile takeover of electrons, it's more like a friendly partnership. Carbon just walks up to another atom and says, hey, let's both chip in some electrons, create a shared pool, and we can both count them towards our stable outer shell. It's a total win-win. This is actually a brilliant way to think about it. The text you see here in Hindi translates to, I'll give you half my samosa. Just imagine you've got this samosa and your friend has some noodles. Neither of you wants to give up your whole lunch, right? So what's the solution? You share. You both get a better meal, you're both happy. That is exactly what carbon does with its electrons. It is the ultimate team player. Now, this whole sharing strategy has some pretty interesting results. While the bonds themselves, the sharing, are super strong, the forces between the molecules that are formed, they're often kind of weak. This means compounds made this way tend to have lower melting and boiling points, and since there aren't any free-floating charged particles, they're usually terrible conductors of electricity. But just sharing electrons? That was only the beginning. That ability unlocked 2 truly unique superpowers that take carbon from just some simple element to the master architect of the entire molecular world. Okay, first up, catenation. This is the absolutely incredible ability for carbon atoms to form strong, stable bonds with, wait for it, other carbon atoms. It can create these long, practically endless chains, which act as the backbone for millions and millions of different compounds. We're talking everything from simple plastics to your complex DNA. And its second superpower is something called tetravalency. Because it has those 4 outer electrons to share, it can form 4 separate covalent bonds at the exact same time. You can picture it like it has 4 hands for friendship, letting it reach out and connect in 4 different directions all at once. This is what allows it to build not just simple chains, but really complex 3-dimensional structures. And when you combine these 2 powers, oh man, the possibilities are just staggering. Carbon can link up to form simple, straight chains. It can create branch chains that look kind of like the limbs of a tree. Or it can even loop back on itself and form these incredibly stable rings. This structural variety, that is the secret to its versatility. So we know carbon is a master builder, but you know what? It's also a master of disguise. Depending on how its atoms are arranged, pure carbon can show up in wildly different forms, and these are called allotropes. It really is all about the arrangement. If you organize carbon atoms into this rigid, interlocking 3D network, you get diamond, the hardest natural substance we know of. But arrange those exact same atoms into flat, hexagonal sheets that can just slide over each other, and you get graphite. It's soft, slippery, and it can even conduct electricity. And then, more recently, we discovered fullerenes, where carbon atoms form a hollow sphere, kind of like a tiny molecular soccer ball. So the main thing to remember here is this. Diamond, graphite, fullerene, they are all 100% pure carbon. The only thing that's different is the architecture. It's the same hero, just wearing a different uniform for a different mission. This mind-blowing versatility is what makes carbon so special. So from an element that seemed chemically stuck in a dead end, carbon figured out how to share. It overcame its limits, unleashed its superpowers, and built the very foundation of life itself. It's in our food, it's in our fuel, it's in our bodies. It has literally built the entire world we know. So the only question left is, with our growing understanding of this incredible architect, what are we going to build with it next?